Hello everyone! This lesson opens a section on public key cryptography, also known as asymmetric cryptography. This lesson will introduce the communication model of public key cryptosystems, explain how one-way functions relate to them, describe Diffie-Hellman key exchange scheme, list the objectives of public key cryptography, and compare it to symmetric cryptography. Public key cryptography has brought cryptography to the new life with its elegant idea. Symmetric cryptosystems use one key for encryption and decryption, while asymmetric cryptosystems use multiple keys, where in current practice it's usually two. As was previously discussed, symmetric cryptosystems have an issue at the key exchange stage. They require a secure channel between parties to share the secret key digitally or physically by a trusted courier. Public key cryptography eliminates the need for a secure channel of communication to transfer a secret, and for the communicating parties to share a secret key in the first place. Symmetric cryptosystems use one key to encrypt and decrypt traffic between two parties. An asymmetric cryptosystem instead deals with two keys per communicating party. Asymmetric cryptography introduces the concept of a public key, which, as its name suggests, does not need to be kept protected and may be shared with other parties over any open channel or even posted freely on your website. The secret has to be kept hidden as its corresponding private key. Exposing the public key does not put the private key or encrypted messages at risk. As opposed to asymmetric algorithms, the sender does not have to share the secret private key with the receiver, only the public key. Each communicating party has their own pair of public key shared with others and a private key kept secret. You may also imagine public key encryption as a locked mailbox outside your house. Anyone who has your address can mail you a letter, but only you with the private key in your pocket can open the box and collect the envelopes. For Alice to receive messages encrypted with an asymmetric cipher, she needs to generate a key pair and send her public key to others, or post it somewhere where they can find it, like a personal website or a company directory profile, etc. Bob, and anyone else who has Alice's public key, can now encrypt messages for Alice as follows. Alice can then decrypt Bob's message with her private key. Similarly, for Alice to respond to Bob, he needs to generate a pair of keys and share the public key as well. Alice can then take Bob's public key and encrypt with it, and Bob decrypts a message with his own private key. The security of asymmetric cryptosystems relies on the existence of one-way functions and trapdoor one-way functions. A one-way function f is easy to compute for any input, but given a specific output value y, it is computationally infeasible to find such input x so that f of x equals to y, that is, to invert f. In asymmetric cryptosystems, public and private key are usually related by some function, where private keys are the domain and public keys are the range. This function should be one-way, so that public key is easy to compute from private key, but private key is computationally infeasible to compute from the public key. An example of a one-way function is multiplication of prime numbers versus factorization of the result. Multiplying two long numbers is practically instant, but factoring back takes much longer. For demonstration purposes, the following attempt fails after 30 seconds. In this example, P and Q would be the private part, and N would be the public part. The security of asymmetric algorithms relies on practical difficulty of various hard number theoretic problems. The RSA algorithm, for instance, relies on the practical difficulty of prime factorization, as just explained, and other algorithms like elliptic curve cryptography, Diffie, Hellman, ElGamal, rely on different problems and one-way functions, particularly in abstract algebra, some of which will be covered later on. Encryption transformations in asymmetric cryptosystems are trapdoor one-way functions. A trapdoor one-way function is a one-way function with the additional property that given some extra information, called the trapdoor information, it becomes easy to find for a given output y and x such that f of x equals to y, that is to invert f. In cryptography, these functions are parameterized on keys. A public key is used to go from the domain, the plaintext, to the range, the ciphertext, and it is easy to encrypt the plaintext with the public key. A private key is used to go from the range to the domain, that is, from the ciphertext to plaintext. The private key is a trapdoor. It should only be known to one party, the intended receiver who should decrypt the ciphertext. For other parties without this trapdoor, it is computationally infeasible to invert the encryption and obtain the plaintext. It is not yet formally proven that one-way functions actually exist, but at the current state of modern cryptography, they are widely believed to exist, with respect to reasonable practical definitions of easy and computationally infeasible. Factorization is one hard problem upon which the existence and security of asymmetric cryptosystems depend, but it's not the only one. Another hard problem useful to cryptography is the discrete logarithm problem. It concerns finding a logarithm of a number within a finite field, particularly a prime field. Prime fields are the fields that have a prime number of members. Prime fields are of great use in asymmetric cryptography, since exponentiation over a prime field is relatively easy, while its inverse, finding the logarithm, is computationally infeasible. Several asymmetric cryptosystems in general use today are based on this problem. The Diffie-Hellman key exchange, the ElGamal, and the elliptic curve cryptosystems, for instance. This section will introduce you to the discrete logarithm problem through the Diffie-Hellman algorithm. The Diffie-Hellman key agreement provided the first practical solution to the key distribution problem of symmetric cryptosystems. It allows two or more parties who have never met in advance or have shared keys to establish a shared secret key by exchanging messages over an open channel. The Diffie-Hellman key agreement is executed as follows. Alice and Bob agree on Diffie-Hellman parameters, a prime modulo p larger than 2, and a base generating element g smaller than p, often prime 2. This step is usually done beforehand, and depending on the implementation, parties may decide the values over an open channel, or they may be hard-coded or sent by a server. For this reason, the modulo and the base are assumed to be known to potential attackers. Next, the parties independently generate a private number each, called x, smaller than p minus 1. So here is the number Alice gets, and this one is Bob's. Next, they both generate public keys y with the formula that y equals the base to the power of x modulo p. So here is the Alice's public number, and here is Bob's. Then, Alice and Bob's exchange the public keys y and each independently compute a shared secret key zeta, where zeta equals to y to the power of x modulo p. So the Alice computes this, and Bob computes the same number. This secret key may then be used as the key for symmetric encryption, for example IAS, to encrypt arbitrary data between the parties. Mathematically, they generate the same value for the shared key, since Alice's public y raised to the power of Bob's private x is equal to their base g raised to the power of Alice's x and Bob's x simultaneously, which in turn is equal to Bob's public y raised to the power of Alice's private x. In terms of the preceding equation, the discrete logarithm problem is finding the private x where only y, j, and modulo p are known. In a finite field with a large enough value of the prime modulo p, this turns out to be infeasible to attempt within a reasonable amount of time, even on the fastest supercomputer. In general case, no efficient non-quantum algorithm is known for finding the discrete logarithm or prime factorization, so cryptosystems based on the difficulty of these problems are utilized for the time being, as long as classical computers are used. Asymmetric cryptography in a post-quantum world will have to make use of different approaches, like lattices or error-correcting codes, that are considered to be secure to attacks by quantum computers. Funding such cryptosystems remains an active research topic nowadays. Originally, the only goal of cryptography was confidentiality, to conceal the information. But with the evolution of the field, it has expanded to provide other security services, such as integrity, authentication, and non-repudiation. Public key cryptography algorithms are versatile enough to be adapted and used together with other cryptographic tools to achieve any of the mentioned objectives. A shared secret key computed with the Diffie-Hellman protocol, for instance, is then used in symmetric encryption like IAS to provide confidentiality. Although Diffie-Hellman key agreement does not itself authenticate the parties, it provides the basis for a variety of protocols with entity authentication. RSA public key encryption may be used on its own for confidentiality, or similarly to the Diffie-Hellman protocol, as a means to exchange the key for later use with symmetric encryption. With certain asymmetric algorithms, it is also possible to encrypt with private key and encrypt with a public key instead, like Alice does here. This way, anyone who has Alice's public key, like Bob, can decrypt it. This message, encrypted with a private key, is basically a digital signature, fundamental in authentication and non-repudiation. Digital signing does not provide confidentiality, because anyone like Bob just did can decrypt it. But it shows that Alice, as the only owner of the private key, is the only person who could have created the signature. The purpose of digital signature is to provide a means for an entity to bind its identity to a piece of information. Digital signatures will be discussed in detail in the next lesson. In a public key cryptosystem, Alice and Bob communicate over an insecure channel, vulnerable to attacks, without ever having met to exchange keys. The basic asymmetric key exchange with RSA or Diffie-Hellman protocols provides protection from passive eavesdroppers, but not from an active adversary capable of intercepting, modifying, or injecting messages into the communication channel. Neither Alice nor Bob has assurances that the other party actually owns the private part of the public key they claim to own, or has not been manipulated by malicious entities in the middle. In the following diagram, the attacker impersonates Bob by sending Alice a public key, which Alice incorrectly assumes to be the public key of Bob, and vice versa. The attacker, the man in the middle, can now intercept encrypted messages from Alice to Bob, decrypt them with its own private key, re-encrypt the message with Bob's public key, and forward to Bob. Methods to authenticate parties and their respective private keys will be covered later in this course. The most important advantage of the public key cryptosystems is the one they were initially designed for. There is no more need for a secure secret key exchange channel. However, public key encryption systems will not simply replace the traditional symmetric encryption just yet. Asymmetric cryptography is based on heavy algebraic computations, and it is considerably slower than normal symmetric ciphers based on bitwise operations and permutations. It is also not suited for large inputs, precisely inputs larger than the length of the key. For example, the most used key length in current practice is 2000 bits for RSA, which is not even enough to encrypt this little snippet of text. You could, of course, encrypt the whole book with RSA by splitting it into single sentences and sending them out separately, but it is a lot of work. Fortunately, this issue is solved by using hybrid encryption schemes that combine symmetric and asymmetric cryptography and employ the best features from both. You will learn about hybrid encryption later in this course, and the next lesson will pay attention to digital signatures.